Let's now take a look at scaling complexity and what are the challenges with respect to continuing node-to-node migration. For almost 3 decades now, the implementation flow has been a sequential set of steps: synthesis, place and route, sign-off. But as we have transitioned from 16 nanometers all the way down to 2 nanometers, the number of effects coming up from the physics layer, coming up from the process layer, which has resulted in significant complexity in terms of implementation, have ballooned. And in order to address this convergence gap, predictability gap, and design effort, we need a new approach to digital design. The traditional approach has really been one which requires a lot of iterations. Designers are having to set very pessimistic margins upfront to model all these downstream effects at advanced nodes. And this has resulted in a lack of convergence, a lack of predictability, and inefficient workflows, all resulting in subpar PPA. The solution to this challenge is to really move to a hyper-converged architecture. How do we bring synthesis, place and route, and sign-off onto a single data model and then benefit from the seamless movement of technologies across the front end and back end? This type of an architecture, which we call fusion, delivers the best PPA, ensures full flow convergence, enables us to minimize margins because we have golden sign-off representation throughout the entire design flow, and significantly accelerate the time to results. On top of this, we have the great opportunity to apply AI to explore a much broader design space in order to optimize PPA. A typical design involves a lot of iterations across floor plans, across different tool settings, different libraries, as well as constraints. And the opportunity to rapidly explore this design space in order to find the optimal PPA points is a great opportunity which helps us to dramatically improve productivity as well as improve the PPA of the design. You all may have seen recently at the Hot Chips conference where Synopsys reported some great gains in applying AI to EDA. And some of the results we presented there shows how applying our DSO.ai technology, we are able to find much more optimal points than previously thought achievable, and also significantly accelerate the time it gets to those optimal points in the design space. So exciting technology, and we are having tremendous traction bringing AI and fusion together at many of our lead customers. But the story doesn't end there. A typical SoC project involves thousands of runs of synthesis, of place and route, of sign-off. And all these runs are generating metrics: timing metrics, power metrics, area metrics, runtime metrics, IR drop metrics. And designers are looking at all these metrics and making decisions about how to implement different blocks. This is a tremendous opportunity as well. If we can bring all these metrics into a big data warehouse and then apply the big data techniques to derive insights and to help designers arrive at better decisions and much faster, that has a direct correlation to improving productivity. So this triple play of fusion as the underlying implementation platform, AI applied on top of fusion to explore a broader design space, and analytics to help designers make high-quality decisions much faster is really the way we want to address the twin challenges of PPA gains as well as productivity. Here is an example of a customer that was designing a high-performance GPU that used all 3 methods on a sub-7 nanometer design. And they were able to not just gain PPA 11% power reduction, which is by any means very impressive, but also be able to achieve it in a much faster way with fewer resources than before. So really, this is a great opportunity for us to address both the PPA elements and the productivity elements.